Welcome to the Department of Physics, Shantipur College. In this lecture, we shall discuss the behavior of particles. I promise not to use any mathematics or calculations in our discussion. So let us begin. The matter we observe in the universe is composed of particles. Every object around us is made up of molecules, which in turn is formed from atoms. Again, atoms themselves consist of electrons, protons and neutrons. In other words, electrons, protons and neutrons are the fundamental building blocks of matter, that is, they are the constituents of matter. Again, for matter to exist, these particles must stick to each other, that is, must be held together, that is, they must interact. Such binding occurs through forces that arise due to the exchange of other particles known as force carriers or exchange particles, namely photons, W bosons, Z bosons, gluons. These exchange particles act as the cement that binds the building blocks, the electrons, protons and neutrons, to form matter. It is important to realize that whether we speak of the building blocks of matter or the cementing forces that hold them together, it is all about particles. The universe is thus a story of particles and their behavior. These particles obey certain fundamental rules. Let us now begin our lecture by examining the rules that these particles follow. Now suppose we are given a certain number of energy states or energy levels. The question is, how will the particles occupy these levels? Will they all crowd into one level? Or will they get distributed at random? Or will they avoid one another while occupying the levels and populate the energy levels one by one? In short, what rules do particles follow while filling the available energy states? And furthermore, will these rules remain the same if we change the temperature of the system? There are three main rules or distributions that particles may follow. One is the Maxwell Boltzmann distribution or statistics. The other two are the Fermi-Dirac distribution or statistics and Bose-Einstein distribution or statistics. Let me once again emphasize that these distributions are simply the rules according to which we can populate or fill, that is, arrange the particles in the available energy states. In our discussion, we shall consider identical particles. For example, we may think of a group of electrons, all electrons being identical. Similarly, we can consider a group of protons and all protons are identical to each other. Or we may take a group of photons which are also identical particles. Let us first consider the Maxwell Boltzmann distribution. According to Maxwell Boltzmann statistics or rule or distribution, identical particles are treated as distinguishable. That is, in an assembly of identical particles, we can identify and differentiate the identical particles as separate entities. In other words, if we confine two identical particles, say two electrons inside a box, Maxwell Boltzmann statistics assumes that we can follow the individual motion of each particle. We can, in principle, track one electron and distinguish it from the other, even though they are physically identical. The natural question that arises is, how is it possible to track two electrons in spite of the fact that they are identical? The reason is very simple and straightforward. Two electrons, or in general two identical particles, can be tracked only if they remain well separated from each other. They might be in a box, but they are apart. In other words, Such individual tracking is possible when the system to which the particles belong is dilute, meaning that the system has a low density. When particles are far apart, they do not interfere with one another, they do not mingle, and their positions and motions can be followed independently. But this immediately leads to another question. Why would the particles maintain such separation? Again, the answer is simple and straightforward. The particles maintain a mutual separation because they have sufficient energy to stay apart from each other. They do not care about one another. They move freely, independently, with their own energy and velocity, almost as if the other particles do not exist. Now, why do the particles have large energy? The answer is again simple, because the system is at a large temperature. At higher temperature, each particle possesses greater kinetic energy. As a result, they move rapidly and remain far apart from one another. This high energy condition prevents them from overlapping or interfering, allowing us to treat them as distinct and trackable, even though they are identical in nature. So we have now logically arrived at the criteria or condition for applying Maxwell Boltzmann rule or statistics or distribution. The system should be of low density and should be at a high temperature. Under these conditions, the particles behave like independent balls, completely oblivious to whether another such ball or particle is present or absent. Each particle moves freely, carrying its own energy without being affected by or interacting with others. Now the next question is, how do we count such identical particles that are distinguishable? We can imagine attaching stickers or labels to the particles, that is, name the particles. For instance, one electron is labeled A and another electron is called B, even though they are physically identical. This is possible because we can track their individual motions, they are well separated and therefore distinguishable in practice. Let us emphasize that the Maxwell Boltzmann rule or distribution is valid only under such conditions when particles have enough energy to remain apart. It obviously fails at low temperatures, especially near absolute zero, where the particles lose energy and no longer have sufficient energy to stay apart. As a result, they come very close to one another, and then it becomes impossible to follow or track the motion of individual particles. The coming together of particles due to their lack of energy also means that the density of the system increases. In other words, the distinguishability of particles is lost under such conditions of low temperature, near absolute zero, and high density. The system can no longer be described then by the Maxwell Boltzmann statistics. The rules that govern their behavior at high temperature cease to hold. Under these conditions, new rules of distribution come into play, rules that are different from Maxwell Boltzmann distribution. What are the new rules? They are called quantum rules or quantum statistics that we shall discuss next. But before stating the quantum rules, let me just mention that the Maxwell Boltzmann statistics or rules can be mathematically written as, where average n represents the average occupancy, that is how many particles sit in an energy level on the average. Beta is 1 by kT, where k is Boltzmann constant. T is temperature of system, which is large, that is different from 0 Kelvin. In fact, well above 0 Kelvin. Mu represents chemical potential, which is the energy that system gains when a particle is added, and E is the energy of level or state. We are not discussing how this expression can be derived because we have already promised to shun mathematics and focus entirely on the physics behind it. I am showing this formula of the Maxwell Boltzmann statistics only to drive home the point that at high temperature and low density, the particles of a system follow a rule that possesses a definite mathematical structure. The rule, as per Maxwell Boltzmann statistics, is that we can fill up the energy states in every possible manner at high temperature, low density, and this we illustrate through two very simple examples.